Okay, thank you very much, and it's a pleasure to be here. I speak Russian, but I will give the lecture in English because of scientific terms that I don't know. So it's a pleasure to be here, and thanks for organizers for organizing this talk. I will be talking about a very new phenomena that is called fast radio bursts, and they are mysterious because we still don't know the origin of these sources. We see a fast radio burst here depicted in this picture, observed by a Parkes telescope in Australia. So a brief summary of facts. Fast radio bursts are a completely new type of transients, and transients are signals that vary with time fast, as we will see today. First FRB was detected recently in 2001, and it was so unusual that only in 2007 it was published. So it was detected in an archival survey of pulsars, not immediately, and it took many years to go through verifications and publish it. Now, fast radio bursts are detected almost every day by world's largest and most sensitive radio telescopes. They are very short, extremely short. The duration typically is just few milliseconds, so you can imagine. And they're extremely bright, almost as bright as a supernovae. We still don't know what their origin is. Despite that we've been observing them for almost 20 years, they're still a mystery. They just don't fit into any theory. And we don't know of any sources that could produce them for sure. There are, of course, theories. That's the job of a theorist to come up with crazy explanations, but we don't have any good guess. We know today that most fast radio bursts come from far away, far behind our galaxy, sometimes from, they were originated 11 gigayears ago, or 2 gigayears ago, and they travel huge cosmological distances from the source to us. Despite that, they're still observed today, which means that they're intrinsically extremely bright. They're also extremely frequent. Today we know that an FRB, 1,000 FRBs happen every day per sky. So from the entire sky, we can collect 1,000 FRBs every day. And they're just one-time event. It's not like a pulsar that repeats periodically. It's a burst that goes off, and then the source is silent. There are only few FRBs that were shown to repeat, but most of them, out of few hundred that we have detected today, have not repeated. And they're called radio bursts because they're observed in the radio regime, actually between 400 megahertz and 1,400 megahertz by radio telescopes. This is an example of one of the largest telescopes with a diameter of 300 meters located in Puerto Rico. So fast radio bursts were first detected in 2001 in archival data of pulsar survey of Magellanic Clouds. And by telescope that is called Parkes radio telescope, it's huge, 64-meter diameter, and this telescope is located in Australia. The reason why radio telescopes are usually located in remote places such as Australian desert or South Africa or Atacama Desert in Chile is because they're super sensitive. They can detect even a mobile phone on the moon. So that they're that sensitive, and they have to be placed into radio-quiet regions to detect cosmological and astrophysical objects. This is an example of the fast radio burst. The signal is shown as a function of frequency on the y-axis and time on the x-axis. And this bright line that you see here is the burst. On this top panel, you see that there is a kind of background, and then we see a burst, and then it goes quiet again. And we will be talking today why it swaps diagonally through this diagram, through the space frequency time space. There is a reason for that. So on this diagram, we see that it's indeed a few milliseconds, and it swaps radio frequencies, in this case, between 1,200 megahertz and 1,500 megahertz. This particular burst was extremely bright, 60 billion times the luminosity of the sun, so you can imagine. And it was just few milliseconds, so just a huge burst of energy. Because it was so unusual, there are no counterparts that we knew before existence of such bursts. Initially, people didn't know if they were astrophysical or maybe some terrestrial interference from radio sources. As I said, the radio telescopes are extremely sensitive. So they actually, the scientists were thinking that maybe radio waves are produced by microwaves, and we know that if we open and close a microwave, a burst of energy in this particular frequency range is produced because there are magnetic fields inside the microwave. So actually, in radio observatories, microwaves are put in Faraday cages, such as this one in Jodrell Bank Radio Telescope Observatory, where one of the world's sensitive telescopes is located, the Lowell telescope. So indeed, there were few observations of fast radio bursts that people originally thought were FRBs that were found to be microwave bursts at Parkes. And that's why also Lorimer's burst, the very first one, this one, it's called the Lorimer burst after the guy who found it. So originally people thought it was just a microwave, and they were referring to this burst as peritons, so some mythological creature that doesn't exist in reality. Fortunately, Lorimer's burst turned out to be the real astrophysical event. So we know that they're astrophysical because nowadays many telescopes around the world detect fast radio bursts. They were just very tricky to detect at first because they're really narrow, and it's hard to find them if you're not looking for them on purpose. So after actually detection of Lorimer's bursts, there were several years when people couldn't find any new FRBs, and it was really weird. But fortunately, in 2013, 4 new FRBs were detected and published, also using Parkes radio telescope here. And then in 2012, a new FRB was detected by Arecibo. This telescope is huge, 300 meters, and it's just carved inside a quarry in Puerto Rico, so it's really fantastic, I think. I think it was featured in one of the movies, The Contact. So this telescope is extremely sensitive, and it has great resolution. It has detected an FRB called 121102, which actually is one of the few repeating FRBs that we have, and I'll talk about it today as well. So nowadays we have a lot of FRBs, and many more are coming online. 78 are actually published and verified, but there are many more in the pipeline. At least 300 events are known, and they're detected by different telescopes around the globe from different locations, which also shows that FRBs are astrophysical and not coming from particular terrestrial radio interference. One of the key telescopes now is Chime, and I will be also talking about it today. It's a cylindrical telescope built of 4 cylinders, and you see people here for scale. It has a huge field of view, so it collects FRBs from a wide area of the sky, but it has very poor localization, and if it detects FRB, it doesn't know where it comes from. Chime recently came online less than a year ago and collected immediately almost 300 FRBs in just a few months, compared to the dearth of FRBs in the first few years after the first detection. Then we have ASCAP, which is also a fundamental instrument for FRBs, and I will also talk about it today. It is composed of 36 telescopes, 12 meters each, located in Australian desert in Western Australia. And it is a very sensitive telescope. It can operate in flight eye mode when each telescope is looking into a different direction, and this multiplies the collecting area of the telescope. We already saw Parkes, which was the telescope that first detected FRBs, Arecibo, JBT in Canada, and Molonglo in Australia. So each one of them saw at least one FRB or many, and throughout years, so starting in 2001 and until today. Also, scientists and researchers who are searching for extraterrestrial intelligence actually contribute to FRB science because they're trying to detect radio signals produced by aliens. And they actually are now very well funded by Russian millionaire Yuri Milner, actually, who lives in the US. Yuri contributed a large chunk of money to this research. That this is a program that runs on the, again, part of these telescopes participating, and he bought off time on these telescopes to particularly search for alien signals. These telescopes are very sensitive, and they can actually hear aircraft if it was on one of the 1,000 stars around us. So that far, they can hear radio signals. And sometimes this research actually report new FRBs and contribute to the program because they just search in the same frequency range and using the same telescopes. If you're interested to learn details about fast radio bursts, there is an online catalog that is always updated, and it is run by one of the main researchers in the field, Emily Petrov, who's in Australia. It's a catalog of all FRBs that are confirmed, and there are many fields that you can look at, for example, central frequency of the burst, bandwidth, which telescope has detected it, since the flux, energy, and so on. So everything is here, and you can play with it. It's really interesting. And right now it has 78 FRBs out of the few hundreds that we know. So by now we know that FRBs are very varied. This is a slide that shows some of them, and we see that there is always a burst present, but otherwise they look very different. For example, this one is very strong, and the background is kind of smooth compared to it. Others are wider. For example, this one is very wide and smoothed out. Most of them are very narrow. And they have been detected throughout years. So this number, for example, 110214, shows the year, the month, and the date of the detection. So you see that there are bursts from year 2011 through 2018 here. And these are not all of them, of course. We also know that they are abundant. As I mentioned, if you build a cosmological model accounting for all galaxies in the universe that we can do using astrophysical modeling, collapse fractions, and star formation rates, then we can actually predict how many FRBs we expect to see from the sky, even including the smallest galaxies to the largest galaxies, and using some scaling relations to translate FRB rate per galaxy from the known sources. We get that there are between 1,000 and 10,000 FRBs per sky per day that we can observe. Of course, some of them would be at very large cosmological distances and be very faint for the current telescopes to detect, but there are future facilities that are already planned that will be sensitive enough to detect these bursts. Most likely, the bursts are produced by star formation activity, and we expect them to follow structure that we see on the sky. So here we see what is called cosmic web, the network of filaments, galaxies, galaxy clusters, and FRBs are emitted along these filaments here and galaxy clusters. So we expect them to follow the structure of star formation activity. Till now, the surveys of FRBs were found kind of by mistake. The first one was found in the archival data of pulsars, and people didn't think that they're serious things, so they were finding them just from other kind of surveys. But now scientists become more interested, and the community becomes more aware in that it's a really cool science, so targeted searches are on the way. So even with these random searches, many FRBs were found. As I mentioned, 300 or so were found by mistake or randomly, and this also shows us that FRBs are very frequent. So if we do a targeted search, we expect to find many of them. So the main question, one of the main questions is where FRBs are coming from. Are they part of our terrestrial activity? Maybe they're produced by something in the magnetosphere of Earth. Are they coming from our own solar system? Maybe they are solar flares or something, or maybe they are created by extra solar planets, or come from our galaxy, or maybe they're coming from distant space. And today we are sure that most of the FRBs are coming from far away in the space. They occasionally can occur in our galaxy, but chances for that are tiny. So to determine what is the origin of FRBs, actually the shape of the signal is the key. This is from the original publication by Lorimer in 2007. And on the insert here, we see the pulse itself. It's very narrow, and this is a noise. And on this diagram, frequency versus time, we see the pulse as a function of frequency and time. This pulse is what is called dispersed, because we see that higher frequencies arrive earlier than lower frequencies. And this feature is actually a key for us to understand what is the distance of FRB sources, between the FRB sources and us. So this fact that there is a diagonal on this plot and not a sharp line tells us that different frequencies travel with different speed across the across the medium. So dispersion is just what we are used to see in rainbow or diamonds. We see that the white line is split into a rainbow of colors. And this is just because every frequency travels with different speed in the medium, and this the refraction works differently as a function of frequency. So as the white light is a mixture of different wavelengths, as we know, enters a prism. It is dispersed, and every frequency has different propagation speed in glass or in the medium. This feature, or the speed of every wavelength, depends on few things. So it's both the length or the path of the light inside the medium. For example, here we see as the light goes through diamond, the dispersion increases. So the difference between different wavelengths and colors increases. But it is also a function of medium itself, properties of medium. For example, here on this panel, there is a regular optical glass versus some weird type of glass. And we see that there is a different distance between different colors depending on the type of the glass. So two things matter: the length of the path and the properties of the medium in which light propagates. Absolutely same thing happens with radio waves in ionized gas or medium. Here we see that in ionized medium, shorter wavelengths move faster than longer wavelengths. Right. And the amount of dispersion, amount of the difference between the path, the arrival time of blue light compared to red light depends on the on how long the path is between the source and the observer. This is a telescope, and also the amount of the properties of the medium itself. So what disperses radio waves is ionized gas. So the denser is the gas, the more dispersion there is. And we define dispersion measure, just a quantitative amount of how much the light is dispersed, by integrating the density of electrons along the line of sight between the source and the telescope. So the longer it's the distance between the source and the telescope, and the denser is the gas, the higher will be dispersion measure. And vice versa, if the source of FRBs is very close to us and the medium is neutral, the light will not be dispersed at all. So we can calculate this dispersion measure or measure it directly from the sources and interpret it in terms of the distance between FRBs and the telescope. And that's what scientists do here. So they can calculate by how much the blue or higher radio frequencies arrive earlier than lower radio frequencies. They can calculate this dispersion measure and then translate it in terms of astronomical distances. For all detected FRBs, dispersion measure varies between a few hundreds to a few thousands. And actually, if you just translate it in terms of distances, it means that FRBs are emitted very far from us, and they travel between 3 to 11 giga-years since the time they were emitted to today, when they are observed. So in terms of cosmological redshift, those of you who know what it is, some of the detected FRBs arrive from a redshift 3, and that's when the star formation actually peaked. So we know that they are cosmological and they can probe interesting events in cosmic history. So this plot shows the dispersion measure divided by the contribution of our galaxy. So some of our galaxy has dense gas and contributes to the total observed dispersion measure of fast radio bursts. So this measure as a function of dispersion measure itself. And we see that for FRBs shown with blue dots here, this measure is greater than 1, which means that they are all extra-galactic, come far away from outside from our galaxy, while other known radio sources, such as rotating radio transients or pulsars shown in red and black, come mostly from inside of our galaxy. So I mentioned Chime, this cylindrical telescope, and it was actually a game changer because it overnight, as soon as it was turned on, started detecting tens and tens FRBs. And what they report today, they probably have many more in their pipeline. They just don't bother to tell anyone anymore because there are just so many of them. So they have detected a few hundred FRBs with high dispersion measures. So again, most of them are coming from far away, from large cosmological distances. And this map shows the distribution of fast radio bursts across the sky. So here I show you the declination versus right ascension. These are just two coordinates on the sky. And we see that FRBs are more or less distributed uniformly along this map. So they're just coming from all around us. They're not coming specifically from the plane of our galaxy, and so they're not correlated with the galaxy, with the Milky Way. And this is another indication that they're cosmological. The color here shows the dispersion measure, again, divided by the dispersion measure of our own galaxy. And for most of them, it's greater than 1. So most of the points here are blue, showing that they are highly extragalactic. This, by the way, is not published. It's from a recent presentation that PI of Chime gave at one of the conferences. I'm actually not sure I can show it. Okay, so if we place FRBs in terms of cosmological distances, this cartoon shows the evolution of the universe starting from the Big Bang, which happened 13.7 gigayears ago. And then the universe undergoes a series of astronomical transitions. At the beginning, there was no matter, it was only energy, and then matter appeared, atoms formed. The universe was first fully ionized, and then neutral atoms were created, so it became highly neutral in the intermediate period when first stars were just were forming. And then actually appearance of stars and galaxies contributed to reionization, what is called, because stars emit photons in the ultraviolet range that can ionize the gas again. So today, all the medium between stars and galaxies is ionized to high percentage. So the observed FRBs actually probe this history already to large cosmological distances from the peak of star formation, and then they can originate in one of these distant galaxies that are observed today by telescopes such as Hubble, for example, or other sensitive telescopes. So hopefully in future, when we have many more of them and more sensitive telescopes detect them from even higher redshifts, we can use them as cosmological probes. One of the interesting implications or applications of fast radio bursts, if they exist at very large cosmological distances, even larger than we see today, is to probe the epoch of reionization. So as I mentioned, the universe was fully ionized at very early times, shortly after Big Bang. Then it became neutral, and then stars started reionizing it. So yellow regions are the regions of ionized gas. So far we detect FRBs from this area when the medium between star-forming regions is fully ionized. And so the dispersion measure increases as FRB for more distant FRBs. So on this panel, we see dispersion measure as a function of the redshift of or distance of fast radio bursts from us. And this dispersion measure grows as FRB is placed at larger cosmological distances. This is again because all the intergalactic medium at that time was ionized, and we just integrate along a larger path. But imagine if FRB is emitted when the universe was still neutral, then the propagation of light from that time to the beginning of the reionization era will not contribute to dispersion measure. And we would see a flattening in this function of dispersion measure versus the location of FRB. So in the future, if we have a bunch of them from very early times, we will see this flattening in this function, and we will be able to constrain theories of reionization, which are poorly constrained today. So here you see red and black different lines, and they're just showing different histories of how fast the universe was reionized by first stars. So potentially it's very useful if we have a lot of them, and there are actually bright perspectives. For example, Square Kilometre array, which is coming online in Australia and South Africa, will be actually sensitive to fast radio bursts at the beginning of the epoch of reionization, if they exist there. So Square Kilometre array will have different antennas covering almost a square kilometer on the ground, extremely sensitive, and also scanning a large portion of radio frequencies. So we hope to observe more FRBs with that telescope. So compared to what we see today, this chunk of the history of the universe, we would go much deeper with Square Kilometre array. So we know that FRBs are coming from large cosmological distances, and we can still see them And so this must tell us that they're intrinsically extremely bright, because if we place a source far away from us, the amount of photons that can be detected in the telescope is decreased, follows this inverse square law. So it drops as a radius squared, just because the photons are distributed around the sphere, and if the telescope has a finite area, it will collect only so much photons. So the further is FRB, the less of its photons reach the telescope. And the fact that we can detect them today means that they're extremely bright when they are created. The FRBs that are seen today are almost as bright as pulsars, and that's why they were detected by pulsar surveys, which means they're about 1 Jansky. But they are 10 to the 6 times further away than pulsars that we know from the dispersion measure. So following this inverse square law, we know that they must be 10 to the 12 times brighter than a pulsar, so tremendously bright. Okay, so if we have a bright source of light, what are energetics of it, and how can we understand where it comes from? I will show you the luminosity function of FRBs. I have already shown, but let's understand it. So luminosity function is the dependence of luminosity on time. And for some sources, it's almost constant. For example, sun is more or less stable. But for other sources like supernovae and FRBs, it varies with time. So this is a luminosity function of sun. We know it's periodic. Sun undergoes periods of brighter, sometimes it's brighter, sometimes it's dimmer, and it varies on the time scale of few years, right? There are periodic oscillations in solar luminosity. Pulsars, which are highly magnetized neutron stars that rotate very quickly, few milliseconds. So it's a star that orbits around itself in few milliseconds super quickly, and it emits a jet of radiation which can be detected. So these pulsars are extremely periodic with time, so their light curve varies in time with very precise periodicity. On the other hand, supernovae are another example of transient. It's not periodic, it's a cataclysmic event. A star explodes, right? It's extremely bright because all the energy of sun goes into this explosion. But the light curves decay on the timescale of many days. For example, these are two types of light curves, type 1a and type 1 and type 2 supernovae, which differ in the amount of chemical elements that goes into it, so the luminosity varies. But for both of these curves, they're extremely bright, 10 billion times brighter than the sun at its maximum. And then this light decays with time on the time scale of a few hundred days. However, supernovae stay bright for even centuries in some cases. In all cases. This is an example of Tycho's supernovae. Tycho Brahe has detected this one, and it was just seen by eye. It was so bright, located in, I forgot in which cluster, Virgo. So anyway, he showed this star here that appeared overnight, and that actually is a supernovae that exploded at the same time. And we can see it still today. This is its remnant. So the star is no longer there, but the remnant is still visible and emits radio waves. So supernovae is a transient that varies on the timescale of centuries. Unlike that, and unlike anything else that I have shown, fast radio bursts seem to be cataclysmic events. They don't repeat, most of them, and they are extremely short radio transients. So that's the light curve of a fast radio burst. So I told you that they are not periodic and probably cataclysmic, but actually few fast radio bursts have repeated. We have detected few that repeat. There is no periodicity in them. They repeat chaotically, sporadically, and that actually makes things even harder. If most FRBs don't repeat and some repeat and randomly, what is their nature? So if we make a simple calculation and compare the energy emitted by the sun supernovae versus fast radio bursts, we can see that actually fast radio burst is intrinsically as bright as supernova. So 10 to the 10 brighter than the sun in some cases, but it's very narrow in time, so the overall energy that is emitted is much smaller than the supernovae. So the supernovae emits about 10 to the 44 joules per unit mass, while fast radio burst emits around 10 to the 33 joules. So overall energy is much smaller, but the brightness, instantaneous brightness at the time of emission is almost the same. So we have many questions to answer with observations, and most of them are not answered yet. Some of the key questions is in what kind of environments are supernovae FRBs produced? What are the progenitors or sources of these bright flares? And if there are several populations or all FRBs are the same, maybe they all repeat and we haven't detected them. So now the community became more interested in that, and more funding went into this research. So there are targeted searches for fast radio bursts. However, most of the telescopes are not really, they're very sensitive, but they're not really, they don't have high resolution. For example, Parkes, that has detected the first FRB, has a beam size of 2 degrees on the sky, which is even larger than the moon. The moon has half a degree size on the sky. So if Parkes detects an FRB, scientists cannot tell where exactly on the sky it happened. We know the precision up to 2 degrees, plus minus a degree. So we can know how many of them there are, but we don't know exactly where they're coming from, and it makes our identification of the host galaxy more difficult. Luckily, some telescopes do have good resolution. For example, Arecibo has it's a very high resolution telescope, and it has detected a very particular kind of FRBs, of a repeater one. The fact that this FRB repeats allowed us to pinpoint the location, identify the galaxy, and also follow up this source by other telescopes. The Arecibo FRB is extra-galactic. It is located at redshift 0.2, and the question is if it's representative or not. So the fact that Arecibo sees many repetitions doesn't mean that other telescopes would also see many repetitions. For example, Chime, when they tried to detect this FRB, they were not able to because they are less sensitive. So Arecibo at the time was seeing repetitions while Chime couldn't. So that's how the FRB host looks like on the Arecibo field of view. This dot is the galaxy where FRB is coming from, shown here also. And this actually, sorry, it's not a Arecibo field of view. It's an image taken by a follow-up very large array telescope that was following up Arecibo observations. So the repeater, this FRB is known as the repeater because at the time it was the only one which was repeating, has this ID number 121102 because it was detected in year 2012 in November. There was a number of follow-ups by different telescopes, both on the ground and in the sky. The very high-resolution VLA telescope. On the sky, there were observations with Chandra and XMM in X-ray bands, and there were optical observations, and various radio telescopes were trying to follow it up. It was actually really a global effort to try to detect the galaxy, identify the galaxy, understand what kind of environment there is, what kind of metallicity, composition, and so on. So unfortunately, X-ray telescopes haven't detected anything, so there is no X-ray emission that goes with this source. Also, not all of the radio telescopes have detected the emission. For example, Effelsberg, which looks at higher radio frequencies, wasn't able to see it, but VLA wasn't. That's how we could identify the galaxy. So this is again the snapshot of this galaxy. It looks like a blob because it's a really tiny galaxy located far away. Here on the sky we can see it also, this little green dot. So these multiple observations have shown that this galaxy is tiny. It has a stellar mass of 5 to the 10 to the 7 solar masses, so it's relatively small. It is very poor in terms of chemical composition, so it is kind of a very primordial galaxy which has not been enriched by supernovae efficiently. It has primordial composition of elements in it. And it's a very unusual galaxy. So most of the galaxies at this redshift at that cosmological time were already much more massive and enriched by metals from supernovae explosions. So this galaxy is similar to Magellanic Clouds. Also, this galaxy is actively forming stars, which is not also trivial. Some of the galaxies are old and don't form stars so efficiently at these redshifts, but this one is small and active. And these observations also showed that FRB resides in a radio nebula, which has magnetized plasma in it. So Chime, this wonderful cylindrical telescope, has since then detected few repeaters. This is a picture of R2, the second repeater, compared to R1, the repeater detected by Arecibo. And we see that there are similarities in terms of this frequency time diagram. There is kind of structure that we still don't understand where it is coming from, but they seem to be originating from the same physical mechanism. So this one is published, but Chime has few more repeaters that they are reporting on at conferences that they have in their pipelines. Because Chime has a very poor localization, it's built so that it has a very wide field of view, but in order to detect many FRBs, but it cannot tell us where they're coming from. Even follow-up experiments and observations could not pin down this FRB, so we don't know still where it is coming from and what type of galaxy it resides. Actually, a week ago, there was another major discovery made by ASCAP, this array of telescopes in Australia. And the discovery was in that they were able to localize a new FRB, even though it wasn't repeating. And this is due to the fact that ASCAP's antennas were looking in different directions, and they can actually follow an FRB from antenna to antenna. And by measuring the delay in time in which an FRB is detected by each one of the antenna, they can reconstruct where it is coming from. So if an FRB is coming from this direction, these antennas would see it first, and then it will appear in these antennas. So that's how they can understand what was the direction of the FRB on the sky. And actually, the localization is very good. 10 arc seconds or so. And ASCAP is looking at the same frequencies as sparks, so 1.3 gigahertz. It has another capability of just looking randomly in the sky. It's called flight eye mode, and this increases its field of view. So this is how this new FRB looks like. It's, again, a typical, very narrow, and very bright. And the surprising thing that it revealed is that the galaxy, the host galaxy of this FRB is a completely different thing from the Arecibo one. In the first repeater, we saw that the galaxy is very small, metal poor, and is actively forming stars. This one shows a different type of galaxy completely. It's an old galaxy with an old stellar population. No new stars are forming almost. And it's also very massive. So the first one was 5 × 10⁷ solar masses. This one is 2 × 10⁻⁻, so 1,000 times more massive in terms of stellar mass. And it's also very enriched by metals and quiet. Also, no repetitions were detected from this FRB at all, so it's probably a different thing from the Arecibo event. It doesn't have this structure as the repeater, so this structure doesn't appear here. It's a very narrow thing. And after ASCAP was able to localize it, many other telescopes looked at it, like DES, VLT, Gemini, and Keck, and they were able to localize and explore the galaxies more in details. They found that the redshift is 0.3, so it's slightly higher than the redshift of the first repeater. And also no radio source was, or magnetized plasma was related to this FRB. So it seems that this FRB and the repeating one are different phenomena and probably are coming from different sources, explained by different processes, or the environments are different. We still don't know. So we are trying to understand how to optimize searches for fast radio bursts. For example, SK, as I mentioned, will be very sensitive, but what is the best strategy to find FRBs? So the question is, if we are looking at the entire population of fast radio bursts, taking into account very distant and faint ones, and also very bright and nearby FRBs, is it better to just look randomly, stare at the cosmic mean beam, or look for fast radio bursts in the cosmic web following the structure near to us? So that's a question we can actually answer quantitatively. This is just to show how frequent FRBs are if we take into account the whole cosmic volume, even the dimmest ones located further away from us. So we expect few thousands FRBs per sky per day, as I mentioned, and these predictions are robust for any model of progenitors and mechanisms that produce FRBs. We know that just because of the amount of FRBs we have already detected. And square kilometer array will be sensitive to FRBs in different wavelength regimes and different distances from us. So the question whether it's best to look for fast radio bursts in clusters of galaxies or in a random cosmological beam depends on the properties of FRBs, such as luminosity function, which is just the distribution of FRBs in the intrinsic luminosity. We don't know if they're kind of like supernovae standard candles, which means they all have the same luminosity, or there is some distribution in the luminosity. So these kind of properties affect predictions and observational strategies strongly. We also still don't know what is the spectrum of FRBs, so the distribution of energy as a function of frequency of the FRB. We have some indications from existing observations, but there is a lot of uncertainty in that. And we also don't know what produces fast radio bursts, so this also adds uncertainty. So if there are many, many faint FRBs in the luminosity function, then it would be really advantageous to look at nearby galaxy clusters. For example, this is a structure of Virgo cluster, which is located just 16 megaparsecs away from us. And it takes up a huge volume on the sky. So because it's so close, even very faint FRBs would be detected if we look at this Virgo cluster and if they exist. And this is again because of this inverse square law. So for nearby FRBs, the photons are not so dispersed, and we can detect them with telescopes. So actually, I made predictions for this, and with Lorimer and his students, we looked at Virgo, and we didn't detect any fast radio bursts in 700 hours. And it straightforwardly means that there are no faint intrinsic FRBs. They're intrinsically very bright. So there is no kind of smooth transition between, at least based on this observation, between pulsars and observed fast radio bursts. So because there are no many faint FRBs, it doesn't matter if you stare at a cluster of galaxies or at an empty cosmological beam. It means that the majority of fast radio bursts would come from large cosmological distances anyway, because they are very bright. In this exploration, we found out that details such as progenitors or spectrum don't matter much. It's just how many faint FRBs versus luminous they are. Okay, and finally, I mentioned that there are no good guesses for what FRBs are, but theorists are trying very hard. So one key feature that we do understand is that because FRBs are so narrow and bright, they should come from a very small region on the sky. They cannot come from the whole galaxy. And this is because coordinated action is needed to produce such a narrow pulse. If a broad region emits radiation, it would be spread in time just because there is no interaction between different parts of a galaxy. So we understand that FRB should be related to some stellar phenomena or something confined to a small region. And actually features in the fast radio bursts show that some of them are coming from an event that is as small as 10 kilometers. So it's a small star or something that creates such bursts. And also we always should keep in mind that we still don't know what fast radio bursts are. So there might be few types of them. In particular, repeaters and non-repeaters seem to be coming from two different types of astrophysical phenomena. So I told you that in principle, fast radio burst is similar to pulsar, except that it doesn't repeat. And pulsars are coming from a neutron star that rotates quickly. A similar emission can come from a magnetosphere of a star that creates pulses and interactions, synchrotron emission, and so on. So there are bursts that we observe in our galaxy of a similar type, but the one thing is that they are 10 to the 12 times dimmer than what we observe from fast radio bursts. So it's hard to think that these two things can be coming from the same origin. But actually, we don't understand the neutron stars that well to be claiming that they cannot, so to rule out this hypothesis. So there are at least 55 different theories that try to explain fast radio bursts, and the origins can be white dwarfs, cosmic strings, superconducting cosmic strings, decaying cosmic strings, magnetars, black holes, and even people were proposing extraterrestrials, spaceships, reflections, and lasers in space, and so on. So theorists are really trying very hard, but still there is no good theory that would describe them all. And I'll stop here. I showed you that fast radio bursts are really interesting new type of sources that we still don't understand. They might be related to magnetars or rotating neutron stars, but there are a few orders of magnitude, 10, 12 orders of magnitude difference in the luminosity between the known objects and the energy of FRBs. There is a wide international effort in detect and characterize these new sources and understand them. And they might be exciting cosmological probes if they are located at high cosmological distances. And once we know how to interpret them and what they are, we will be able to use them for cosmology. Thank you very much for your attention.
Если у вас есть вопросы, поднимайте руку, я к вам подойду.
Thank you for the lecture.
Можно, I don't know.
Ну ладно, прям на русском можно?
Да, на русском.
Спасибо за лекцию, очень интересно было вас слушать. Вопросик следующий. Есть ли у нас в обозримом будущем вообще какой-либо шанс найти какие-нибудь разумные, не знаю, цивилизации? Ну ладно, что-нибудь, хотя бы какую-то жизнь
Okay.
в наших галактике?
Thanks for the question.
Бесконечные. Это только первая часть вопроса.
So the question is if there is any chance to find intelligent life in our galaxy in near future. And of course, I'm not the guy, I don't know, but there is a...
По вашему мнению?
In my opinion, yes, because there is an active research and search for extraterrestrials, and the world's most sensitive telescopes are being used for that, and more and more people in the community become interested in that. Also, Square Kilometre Array, which is coming online in a few years, it has a program, a science case to study and search for signals, for artificial signals. So scientific community, at least part of it, is very interested in pushing for this exploration, and also there is funding, which is crucial in terms of instrumentation and just human resources, right? So there is funding for that research. So if they exist, then there are chances.
Ну, то есть шансы довольно-таки большие, по вашему мнению.
I don't know how to the question is if the chances are large or not. I don't know how to because we don't know if they exist and what kind of life forms are they.
Ну, то есть подключаются ученые, более прогрессивное оборудование, сейчас искусственный интеллект еще подключен, нейронные сети, и найдем кого-нибудь. А если мы найдем, то не боитесь ли вы, что это будет более разумная цивилизация, которая в конечном итоге, ну, как бы уничтожит человечество? Ну, просто мы повторим судьбу индейцев, которых вот приехали как бы европейские конкистадоры, просто поработили.
The question is if I'm not scared that the alien civilization will be more advanced than us and will destroy us. I would say that no, because if they were, or if they are more intelligent, then they already are. They don't need us to find them in order to destroy us, in my opinion.
So,
thank you.
Next question, maybe. You were talking that the repeaters are probably having another nature than single bursts, and the repeaters, they don't have any system in their pulses, right? They just randomly pulse.
Yes, that's right.
And what if, maybe someone checked or not, what if those random placed repeaters have some mathematical correspondence within them? I mean, single one doesn't have any, but if we connect them all, maybe they have some mathematical correspondence.
Thanks. they don't seem, I think people were checking for that, and they don't seem to have any dependence, any sequence.
So it just wasn't checked, or just you
I think
have
people
proof?
are trying to understand that and are checking for that, but the bursts are, sometimes it's quiet for months and then there are many of them going off, and sometimes there are single bursts, and so it's, nobody has found the sequence.
Maybe if we find more and more repeaters, maybe we can find some correspondence between
Yes,
them all.
that's a plan. That's why people are searching for them and trying to monitor. And they are actively searching for repeaters by revisiting the same fields many times with telescopes, and very few are found because high sensitivity is needed for that.
It's just the nature, the probability of other nature of these repeaters that bothers me. Maybe there's just that very thing we're searching in SETI program.
Maybe we don't
this
know,
other
right?
nature.
So, and maybe it could be that some repetitions are fainter than others, and we don't see them because they're below the detection threshold of the telescopes. So it's hard to establish sequence if part of the information is missing.
Thank you.
Thanks.
Здравствуйте, спасибо за лекцию. А применялись ли при исследовании ФРБ так называемая функция неопределенности, unambiguous function, которую открыл Вудвард? Она просто хорошо применяется в пассивной и активной локации для определения координат пространственных и скоростных характеристик целей, когда, собственно говоря, у них там идет определение. Возможно, это могло бы и здесь, ну, если такие исследования проводились.
I'm not aware of this, if it has been used or not, the localization, Woodrow localization function?
Unambiguous function used in radar techniques for localization of target. So if FRB is radio source, that this function can used for localization and velocity determination.
Thanks. I'm not aware of whether experimentalists were using it or not.
Thank you.
Thanks.
Thanks for the lecture. I was wondering how accurate or how reliable are the models that people use for the plasma that's along the line of sight between us and the FRBs that we use to tell the distance or the redshift?
Right. Thanks. That's a great question. And at the moment, they're not very precise because there is no need. There are many uncertainties that are from observations. For example, dispersion measure is known up to a few hundreds because we don't know what is the dispersion contributed by the host galaxy. In most cases, we cannot measure that. We measure the whole thing. So there is no point in verifying the electron density modeling. But as long as far as we go on with this exploration, the better modeling needs to be done. For example, if you are talking about high redshift FRBs, helium ionization should be included. And also inhomogeneities in plasma along the line of sight should also be taken into account. Thanks.
Thank you.
I'm sorry, this might be a stupid one, but how consistent are the repeaters in terms of frequency magnitude characteristics and some other properties? Because as far as I understood, with current angle resolution, we could not distinguish a repeating one from two different events of similar nature. So maybe there is like the galaxy or the cluster, which is going through the epoch where it's just the emergence of this kind of events is just peaking. Can we distinguish this from a repeating event of the same source, or there are just different similar sources?
Yes, thanks for the question. It's the chance of having two sources very close together is small if they're not the same. So the smaller volume you consider, the smaller is the probability that they are coming from totally different sources. But the repeater one shows various different, the pulses are very different, so they can dance around the central frequency and magnitude. But that probably comes from the properties of host. For example, if there is something rotating, the plasma can have inhomogeneity, so turbulence, and that would affect the scattering of FRB along the line of sight, contributing to these differences between various pulses. Thank you.
Такой будет немного специфический вопрос. У вас везде, ну, как бы сказать, там, везде вы показывали спектры, где у вас частота и время, условно говоря, откладывается. Есть ли какие-нибудь исследования, допустим, где применяются для анализа данных видов сигналов, допустим, wavelet преобразование? Дело в том, что это преобразование, оно дает возможность детектировать и по частоте, и по как бы заданной длительности и масштабу. Вот. Возможно, его применение для вот таких исследований позволило бы увеличить, так сказать, вероятность попадания на какой-нибудь из вот этих вот случайных событий.
Yeah, the question is if wavelets are used. I think they're used. It's nowadays it's a common tool in data analysis, and the scientific community is aware of this. It's one of the tools along with Fourier transforms that scientists are using. So I think they're using them, even though I don't remember a paper in which it's reported.
Следующий вопрос. Вижу. Передайте, пожалуйста.
Спасибо большое за лекцию. Я бы хотела спросить про график светимости в зависимости от времени. Он существенно отличается от вот тех объектов, которые до этого исследованы. И вы говорили про теории. Есть ли ограничения вот этого графика в зависимости от данных, которые мы получили, на вот такие экзотические объекты? Либо все-таки вот эта теория дает возможность полагать, что это, например, тот же самый магнитар или какие-то другие объекты?
Thanks for the question. The question is whether the luminosity, the light curve, can help us to distinguish between different theories, right? So yes, of course, all these theories try to explain the observation. So they all are built so their light curves are as the observed ones. So I hope I answered your question. And if there is a new observation with a slightly different light curve that doesn't fit one of these theories, that doesn't match, then that's a way to rule these theories out. And the theories are ruled out as more and more observations are accumulated. So every one of these models listed fits the light curves well. Okay, thanks.
Все, я вас поняла. Спасибо большое.
Добрый день. Хотелось бы знать, есть ли зависимость в частоте событий, происходящих этих вспышек, от направления к центру Вселенной?
Thanks for the question is whether there is a dependence of the event rate as a function of the location on the sky. So as I showed here in one of the plots, the secret one from, well, it's not secret, it was shown in a conference, so it shouldn't be secret. So here we see the distribution of fast radio bursts as a function of the galactic coordinates, declination and right ascension, and at least what Chime can see, there is no dependence with the line of sight, so there is no preference to the galactic center.
Центр галактики или Вселенной?
So if it's the galactic center or the center of the universe, so in the Big Bang model, there is no center of the universe. It all expands in all directions, so you cannot pinpoint the center, actually.
Спасибо. Thank you for your election. Please excuse me, maybe I misheard in the beginning of the election, but anyway, my question is, are there any FRBs that were detected by different telescopes at the same time?
Yes, of course.
How many?
Well,
1, 2, 3?
No, just one actually.
Majority or minority?
So only one FRB, the repeater, as far as I know. Because it repeats and because people know where it is exactly, it has been detected by many telescopes at the same time. So here there are repetitions. So this top panel shows different repetitions of this FRB because it was repeating. And the horizontal lines are different telescopes. And there are circles when few telescopes were detecting it. Other FRBs, they don't repeat. And they're so short that it's hard to follow them up immediately because telescopes have reaction time. And even though the community is well synchronized, so they send announcement to each one of them, to each other as soon as they detect FRB, it's very hard to go there immediately and detect the same one.
So it's not a fraud story?
Sorry?
It's not a fraud story.
Oh, no, this one, no, it's real. It's been detected by many telescopes. And so originally it was detected by this Arecibo one in the hillside. But then telescopes such as VLA, this one has, well, this one has followed up the galaxy, but LWA was, so Arecibo and VLA were detecting it for a few times.
Thanks.
So yeah, I don't think it's a fraud story. Yeah.
Sorry.
Есть ли еще руки?
Thank you for the lecture. I have two simple questions. What is your favorite star? It's the first question. And the next question, what is the favorite part of your job?
Oh, that's not related to the lecture at all. So, I mean, no, that's my favorite stars. I like all of them.
Oh,
so I
so
like
cute.
Sirius, it's really nice.
Oh.
And the favorite part of the job is just doing science. It's really exciting and learning new things every day. And every field, I work in few fields, and every one of them is changing very quickly, and it's really exciting.
Thank you, you're awesome.
Еще вопросы? Передайте, пожалуйста, девушке.
Спасибо большое за лекцию. Скажите, пожалуйста, а как планируется повышать чувствительность этих радиотелескопов? Может быть, их в космос выводить или, например, на другие планеты?
Okay, thanks for the question was how to increase the sensitivity of telescopes and if it's possible to put them in space or other planets. Indeed, there are, first of all, putting telescopes in space already gives a better sensitivity because many times, especially with radio observations, ionosphere of Earth actually gets in the way, in particular at low radio frequencies. For telescopes such as VLA, I think the size of the dishes increases the collecting area, so the bigger the better. And this one, Arecibo, has a very large dish, and it collects a lot of photons, so it's more sensitive than Parkes, for example. Also, putting many telescopes together effectively increases the area and sensitivity. Just placing the same telescope in space will not improve in terms of sensitivity. It will help to avoid the interference of ionosphere, but not the proper sensitivity on its own. What else? The electronics and the quality of mirrors for space telescopes, for example, X-ray telescopes, the technology helps. So the more advanced is the technology for making mirrors, for example, or the more sensitive electronics, the better. Because eventually, if a photon is detected, it needs to be multiplied by the electronical chain. I forgot the name. Photon multiplier, and then the signal is larger. So there are various things, and I'm a theorist, by the way. I don't know. Yes, so square kilometer array should be more sensitive than any of them. And that comes in terms of collecting area. It will have a lot of dishes. So it increases the area, but also the design of the dishes themselves helps sensitivity. That's what I can say about it.
Спасибо.
Да, есть ли еще? Только покороче.
Можно.
Я хотела бы спросить, поначалу квазары путались с этими быстрыми радиовсплесками, или как-то вот они связаны? Вы можете объяснить поподробнее, как отличить квазар от этих самых всплесков?
Well, the question is whether quasars can be confused with fast radio bursts, and no, actually, because quasars have different properties in their emission. They produce radiation that is more stable than fast radio bursts. So in terms of fast radio bursts are really short, right? They're millisecond pulses, while quasars are luminous along in larger periods of time. They're just there. There is a black hole sitting in the center of our galaxy, for example, or other galaxy, and it accretes matter all the time. It doesn't last just a millisecond. It's a more continuous radiation. Thanks.
Okay, thank you very much. Can you say something about the polarization of fast radio bursts?
Right, thanks for the question. I didn't go through polarization. It's a kind of new thing because most of the surveys were not looking in polarization. But some of them are found to be polarized to to like 10-20%. I don't remember. I didn't look into that today. So I can send you some links if you're interested.
Есть ли еще вопросы? Выше держите руку, иначе я не вижу.
Такой вопрос. Есть ли вероятность, что, допустим, часть вот этих вот всплесков являются, по сути, электрическими разрядами атмосферными, которые происходят непосредственно на Земле? Вот. Это тоже очень короткие явления с очень широким спектром частот.
Thanks for the question. The question was whether this fast radio bursts can originate in can you repeat in the Earth?
Разряды атмосферного электричества, ну, молния, гроза.
So like lightnings on Earth, and I think today we know that they come from space, in particular from dispersion measure, right? I showed you that the dispersion measure that you can calculate from this diagram is usually very large, so it can be few thousandths parsec per centimeter cubed. And in all models, scientists do take into account contribution of our galaxy and all known components. In all models, this is much larger than what you expect from the entire galaxy, not just from lightnings. So this is, of course, a possibility, but I think today we rule it out. And also there are two FRBs that have been localized, and they show, we know what are the galaxies they're coming from. So they're located at very large cosmological distances. We know the redshift and so on.
Так, есть ли еще? Видимо, нет.
The question is if the time of the burst takes half a minute. So at every particular frequency, the burst takes just few milliseconds. But so that's the deep black line here. So for example, at frequency of 1.2 gigahertz, it takes just this part of the, just that small fraction, right? What takes half a second is the arrival time of the entire pulse. And because high frequencies arrive first and lower frequencies arrive later, the pulse is kind of smeared because of the dispersion.